Hi everyone, I am Luowen Qian from Boston University, and today I am here to present our work on lower bounds for function inversion with quantum advice. And this is joint work with Chung and Tai-Ning Liao. So let me just start by introducing the problem of function inversion, which is tightly associated with the cryptographic primitive of one-way functions. Informally, one-way functions are just functions that are easy to evaluate and hard to invert. Here, we denote the size of the domain for these functions as big N, which is exponential in the length of its input and output. One-way functions are foundational for the theory of cryptography, where we usually characterize hardness by asymptotic statements like polynomial time adversaries, as we have seen here, where we say the function is easy to evaluate if it takes only polynomial time to evaluate it on a Turing machine, and we say it's hard to invert if any Turing machine or algorithm cannot invert it correctly in polynomial time. However, when we use these cryptographic schemes in practice, separating hardness via only polynomials is clearly insufficient. For example, let's say I have designed a candidate one-way function. I would like to know how I should pick my domain sizes so that it can guard off any reasonable adversary trying to attack it. We can also view this problem as follows. Let's say we have a function mapping 128 bits to 128 bits. I would like to know what is the best generic function inversion algorithm or attack against one-way functions. Here, by generic, I simply mean that the algorithm should work for every, or at least almost every function. Obviously, if we simply use the naive algorithm, exhaustive search, it is going to take time roughly on the order of 2 to the 128, which seems like a long time. But since this description of the function is public, another pretty naive thing we can try is to simply pre-process the entire truth table of the inverse of the function. Of course, this truth table will still be of size roughly 2 to the 128, but once we have done that, we can simply invert any output with a single query to our preprocessed truth table. In 1980, Hellman proposed an algorithm, subsequently analyzed by Fiat and Naur in 1991, that shows that we can achieve a trade-off between preprocessed space and inversion time. In particular, they show that we can achieve where both the time and the preprocessed space is only of order 2 to the 96, which is an improvement from what we had before, which is 2 to the 128. Finally, in 1996, Grover discovered the quantum search algorithm, which shows that this problem can be solved by quantum computers much faster. In particular, for function inversion, a quantum computer only needs time roughly 2 to the 64. So a natural problem lurking in the shadow is that maybe there are some algorithms that can actually generically invert any function using resources only of size 2 to the 32, which would be very worrisome for cryptography. And in fact, an actual direction for better algorithms is simply trying to combine Hellman's preprocessing algorithm with quantum power, as we have witnessed by Grover's search algorithm. In this work, we investigate deeper into this intriguing possibility, but first, let me summarize about the known results. So for inverting random functions, the algorithms we mentioned before, namely Hellman's algorithm and Grover's algorithm, achieves time order of n over s squared and square root of n respectively. Furthermore, we have also known that these are more or less tight in their respective regime since the last century. That is, classical preprocessing algorithms require time at least n over s, and quantum algorithms without preprocessing power requires time square root of n. Again, this leaves open the possibility of quantum preprocessing algorithms, but first let me explain more specifically what we should mean by quantum preprocessing. Similar to its classical counterpart, the easiest way to formalize quantum preprocessing is to think of a uniform quantum circuit with length t, but additionally the circuit also takes an advice of size s as input. The advice can be either classical or quantum. For the simpler classical case, the advice will simply be a bit string of s bits. But more generally, the adversary could also prepare a quantum state of s qubits, which might allow him to invert functions much faster. For the case of classical advice, Naive, Aronson, Belos, and Trevison in 2015 proved that using time square root of n over s is required for inverting permutations, which is a slightly different distribution than inverting random functions. Independently by Han, Kusagawa, and Yamakawa in 2019, they proved that this exact same lower bound also holds for inverting functions. Furthermore, they also extended the permutation case to handle quantum advice. So in this work, we show that for the general case of quantum advice, this lower bound holds generically for both inverting functions and permutations. Before diving into the technical details, let me first interpret these bounds using the following graph. So in this graph, the preprocessed space is on the x-axis, where we have no space, having space of n to the fourth, square root of n, and so on. On the y-axis, we have the running time of the algorithm. And this region here captures all the regimes that some algorithm is able to achieve non-trivial speedups, as we have discussed before the trivial algorithm achieving s equals n and t equals n respectively. So first, Hellman's algorithm for random functions achieving trade-off s squared t less than n squared is plotted as this black line. Next, we have Liao's lower bound of st greater than n, represented by this dashed line on the graph, and the gap between these two lines is the regime where we don't know if there exist better classical algorithms. Moving on to quantum algorithms, Grover's search achieving time square root of n is represented by this red line on the graph. And the quantum lower bounds we discussed before is st squared greater than n, represented by this blue line, can also be informally interpreted as the best straight line lower bound that we can hope to achieve on this graph. Now I want to give you some flavors of the ideas of proving this lower bound for the general quantum advice case. Before we start, it is good to recall the compression argument, also sometimes known as the incompressibility argument, which is the common idea for proving these lower bounds. For simplicity, we will only focus on the case of permutations, which will contain the more important ideas of our proof. So we can think of permutation inversion as the following game. On the left-hand side here, we have the truth table of the permutation pi. Once we have determined this permutation pi, some advice, which we denote as alpha, is preprocessed and fed to the adversary, and then a random entry x mapping to y is sampled from the truth table, and the image y is sent to the adversary as his challenge. Next, the adversary makes some queries to the truth table, and finally he outputs his answer x prime. The idea of compression argument is that if the adversary is very good at this game, we should also be able to use his advice and his code to design a very good encoding scheme for the permutation. And we finally can complete the proof by simply invoking the incompressibility of random permutations. On the high level, the encoding scheme can be summarized as follows. We first take the entire permutation truth table along with the preprocessed advice for this permutation, assuming classical advice for now, but we randomly remove a small fraction of entries from the table. On the high level, as we are only removing a small fraction, the adversary shall not be able to tell the difference. Next, we ask the adversary to recover the missing entries one by one using the partial truth table that we have prepared, which should allow us to recover the entire truth table back with some decent probability. Now we need to decide how many entries we need to remove. Let's say that we remove k entries, then we obtain an encoding of size, ignoring lower order terms, roughly log of n minus k factorial plus s. Using the incompressibility theorem that says that any randomized encoding with success probability delta cannot compress a random permutation table into fewer than log of delta n factorial bits. If we set k to be roughly n over t, or equivalently we are removing 1 over t fraction of the table, we obtain the lower bound s times t greater than n for classical randomized algorithms, which recovers Liao's bound for classical preprocessing algorithms. If we instead remove 1 over t squared fraction of the table, which this t squared term corresponding to Grover's search algorithm, we obtain the lower bound s times t squared greater than n for quantum algorithms, as was shown by Nayabi et al. However, it seems unclear how to extend this argument to the quantum advice case. In particular, the compression argument requires reusing advice. Recall that the coding algorithm needs to invoke the adversary for every deleted entry and subsequently measure the output in order to recover the entire permutation truth table. However, the famous quantum no-cloning theorem says that we cannot clone or reuse a quantum advice multiple times. To see this problem in our context, consider the following adversary who has prepared simply a plus state as its advice, and he is simply going to use this plus state to do two things. First, he is going to check that the state is not touched. In particular, he is going to measure in the plus-minus spaces and check it's still in the plus spaces. And second, he is going to use it to output 1 out of 2 pre-images that he has found via, say, exhaustive search, via a simple control swap operation. For this algorithm, we can see that if we naively measure his output and then rewind his computation, with probability a half, he is going to terminate for the next round, which means that our decoder success probability is going to drop exponentially. The way we get around this advice reusing barrier is the following idea. Instead of reducing the problem to compression, which inherently requires us to invoke the adversary multiple times, we instead reduce it to another problem called quantum random access code, introduced by Ambinis, Nayak, Tashma, and Varzirani in 1999. On a high level, quantum random access code also compresses a long string into a quantum state, but we are only asked to recover a random entry correctly with high probability instead of recovering the entire truth table. In their work, they show that a quantum random access code that compresses n uniformly random bit stream into m qubits with decoding success probability delta over trace of random string and random index has to satisfy that m has to be greater or equal to delta times n. So there are two issues with using this quantum random access code definition with our compression argument. The first is that this delta times n term, which is equivalent to delta times log of 2 to the n, is significantly worse than what we have for randomized encoding of truth table, which is roughly log of delta times 2 to the n. And the second issue is that even for the case of inverting permutations, each element is not independently distributed, as every two elements in the permutation has to be disjoint. Let's first look at the encoding length problem. We observe that the encoding length of quantum random access code, which is delta times log of n factorial, is actually very close to the encoding length of randomized encoding, which is log of delta times n factorial in the regime where delta is very close to 1. So in order to get around the bad encoding length problem, we can just boost the success probability of our encoding using the following procedure. We start by taking the original advice and prepare k independent copies, where k is roughly of order log n. And this would cost us roughly s times k qubits for our advice storage. And to invert an image, we just use these k independent copies and run the algorithm k times in parallel, which we would require t times k queries. And finally, we just output the majority votes of all the algorithm outputs. And to resolve the problem of correlations between the elements of each entry, we developed a generalized quantum random access code, which allows you to compress n arbitrary random variables. Furthermore, the length of the encoding can also be variable. The bound that was presented here is a bit simplified, which says that the average encoding length L has to be at least delta times the entropy of x, which corresponds to the original lower bound, minus a small term of n times h of delta, where h is the binary entropy function. So this is a small loss term, which at the end of the day makes the calculations of our proof somewhat more involved. And the proof of this theorem follows from several properties of von Neumann entropy, like strong subadditivity. We believe the generalized quantum random access code notion we developed here might find other applications in quantum information theory and quantum computations. In interest of time, we swept a lot of technical complications under the rug, and we encourage interested audience to read our formal technical treatment in our paper. So to conclude, our work showed that the lower bound of s times t squared greater than n is required to invert both random permutations as well as random functions, and the techniques we use are compression argument with a generalized notion of quantum random access code. We note that the work of Han, Kusagawa, Yamakawa achieved the same lower bound, but only against random permutations, and their techniques are also using compression argument, but instead of using it with quantum random access code, they instead use gentle measurements to recover the entire permutation truth table. Finally, Tai-Ning, Liao, Qipeng, and me recently posted a new preprint achieving a tighter lower bound, which is s times t plus t squared greater than n against random functions. Furthermore, this result holds for arbitrary domains. So in particular, it also holds for a hash function mapping, say, 256 bits to 128 bits. This new bound can be seen in the following graph as the new red line, which matches both Grover's search algorithm and classical lower bound. And that concludes my talk of proving lower bounds for inverting random functions and permutations. Thank you for your time.